In this video, we'll study reactance with respect to an inductor. So the reactance in simple words means measure of opposition to the flow of current. So if the reactance is large, it's more difficult to flow current. If the reactance is small, it's easier to flow current through the element. So now that's what a resistor is also in a way, because that also measures opposition to the flow of current. In case of a resistor, the resistance R is given by voltage across the resistor divided by the current across it. So now clearly this is independent of time, and this can be defined in such a way. But in the case of an inductor or a capacitor, the voltages and current through it are a function of time, and defining them in a way similar to a resistor is not meaningful because it has a time dependence. So the for the case of an inductor, to see how what does a reactance means, we go back to its uh, the fundamental equation for the inductor voltage and current relation. So shown here, if we have an inductor with a voltage V applied across it, the current flowing through this is given by the relation V is equal to L into di by dt. So now if we take the current, so can be obtained by integration of the voltage across the inductor. So in this case, it is shown by 1 by L integral of V dt, with it may have some initial current flowing through the inductor. So if we take a example of a sinusoidal signal, which is a voltage source applied across an inductor. So in this case, if we take V of t is equal to A times cos of omega t. So if we apply a sinusoidal voltage across the inductor, the current through this is obtained by integrating this voltage, and which is shown here, assuming the initial current through the inductor is zero. So what this shows is that if a voltage V of t is equal to A cos omega t is applied across an inductor, the current flowing through this is A by omega L sine of omega t. And this is how it is used to define an inductor. So instead of defining it as independent of time, we define it as the ratio of the amplitudes, so of the voltages and the currents. So in this case, the voltage amplitude is A, the current that is flowing through this is A by omega L. So if we look at this, it means that if we have take the ratio of the voltage amplitude and the current amplitude, the value that we get is omega L. So this is the magnitude of the reactance, which basically says that if we have a certain amplitude of voltage across the inductor, what will be the amplitude of the current at the same frequency. And from looking at this, we can easily see that as the frequency increases, the reactance also increases, which means that at a higher frequency, it has a higher reactance, and it's more difficult for the current to flow through an inductor. But besides amplitude, there is an additional thing that the reactance does to a voltage when compared to a resistor. So if we had a resistor and applied a voltage A times cos of omega t, the current through this resistor would just have been a scaled version A times cos of omega t by R, if the resistance was denoted by R. But in case of an inductor, it has not only changed the amplitude, it has also changed the phase, cos of omega t to sine of omega t. And the change of this phase is 90 degree, which basically says that the current is now lagging the voltage by 90 degree. So if we had a voltage like this is A of cos of omega t. The current through the inductor is A by omega L sine of omega t, which is basically in a way this is like lagging by 90 degree, which means that when V of t reaches 0, it reaches after a 90 degree phase to the peak. And when this V of t reaches 90 degree, on the reverse side when it reaches peak, it goes to 0. So in a way, it's delayed by 90 degree. and that delay is in complex numbers is denoted by J. So in complex numbers, because we define the current I of t equal to V of t by the reactance of an inductor, and we know that the magnitude of the reactance of an inductor from the above is omega L, but we also want that this current should be delayed by 90 degree. So in that case, if we denote the reactance by J times omega L, so in the language of complex numbers, this would mean that the current I of t would be delayed by 90 degree, and its amplitude will be A times omega L into sine of omega t. So the significance of J is there is the change in the phase from cos to sine of omega t. So that is why the reactance of an inductor is defined as J times omega L, where omega L is the scaling of the amplitude and J denotes to the change in the phase of the current.